Welcome back for 3 more examples of the chain rule for differentiation. This is version 2 of the chain rule. What a person should note here that this chain rule is used to take the derivative of a composition function. So I've written this here as f of g of x. So function g has been plugged into function f. And if we differentiate, we will get a product of 2 derivatives. This first derivative, f prime, is going to be evaluated at the function g, and then we just multiply by g prime of x. Okay. The 3 examples we're going to look at, I'll show you here ahead of time in case you want to just write them down. Maybe you want to pause, jot them down for later. Example 1 will be a composition of a polynomial and a power. So it's this polynomial to the 8th power. If you stare at this a moment, example 2 is also a polynomial to the power, but that power would be a fractional exponent. Can you tell what that fraction would be? Yeah, let's jot that down real quick. So we would have the polynomial 4x minus 7 raised to the 1/3 power. Okay. And then example 3, I make this a little more involved by taking a quotient, a rational function, raised to a power. And I've also chosen to let the independent variable be t, because sometimes our functions are functions of time. Okay, I'm going to try to go through this theorem quickly, as I showed it before in the first video. The chain rule is a theorem about differentiation. So suppose g is differentiable at some value x, and let's also suppose y is some function of u where u is differentiable at any value g of x. The composition function y equals f of g of x is also differentiable at x, and its derivative can be written one of 2 ways. Okay. Version 1 I've written here in Leibniz notation. That's what I did 3 examples of this in the first video. But we label the derivative of y with respect to x this way. And we calculate the derivative as a product dy du times du dx. The derivative of a composition ends up being a product. So version 2 of the same rule should say the same thing with different labels. The derivative of the composition ends up being a product. The derivative of the outside function times the derivative of the inside function. Derivative of the outside, that's f, times the derivative of the inside function, which we'll call g. And then in red, I remind us that we have to plug g of x back into f prime at the end, and I will demonstrate that. Alright, example 1. Let me move this out of the way and get a fresh piece of paper back out here. Sorry for that clean table there. Here we go. We're going to take the derivative of this polynomial to the 8th power. The first thing we want to do is label the innermost function. In this scenario, we're going to label the innermost function g. And so that's that 3rd degree polynomial. Next, we'll take the derivative of g. So we use the power rule and get 15x squared plus the derivative of 6x, which would just be its coefficient 6. And the derivative of negative 19? Well, that would just be 0. So we're left with 2 terms in the derivative. So we took the derivative of the innermost function, and then we turn our attention to the outermost function. So what's the outermost function? Well, we have this power of 8. Everything's being raised to the 8th power. So f of u will define as u to the 8th. F prime of u would be 8u to the 7th power. And now here's where we need to plug in our function g into f prime. Okay, so since f prime of u is 8 times u to the 7th, f prime of g is going to be 8 times g to the 7th. And if we look back at the top, g was that polynomial, the third degree polynomial, which I'll denote in red. And so these are the pieces of the puzzle. Our derivative is going to be a product, g prime of x times f prime evaluated at g. We'll have the second degree polynomial times this power to the 7th. Okay. And let's see how this is going to work out. I'll remind us of the rule, and we'll put our two calculations together to get our derivative. Okay. Again, the rule. The derivative of a composition ends up being a product. Essentially, it's f prime times g prime. But here in red, I'm emphasizing that we got to plug g of x back into f prime. Okay. So final answer, the derivative of the polynomial to the 8th power is 8 times the polynomial to the 7th times 15x plus 6, the derivative of the innermost function. Okay. Just to take a break just a second and look at this answer. Eventually, we just want to train ourselves to look at this power of the polynomial and generalize what we know about the power rule. So in practice, we'll probably just bring down the 8, leave the base, subtract 1 from the exponent, but we can't forget to multiply by the derivative of the innermost function. So those are the essentials in the nutshell. All right, let's move on to our next example. We're going to take the derivative of a cube root function. And I'm going to have to change that paper. There it comes. Okay, example 2. The derivative of the cube root of 4x minus 7. Okay, as we talked about on the first slide, the cube root of this polynomial can be written as a power where the exponent is 1/3. So now this should remind us of example 1. We look for the innermost function, which is that polynomial 4x minus 7. And we might as well go ahead and take the derivative of that function. Well, that would simply be 4, the slope of that line. Then we look for the outermost function. What's being done to that linear function? Well, we're taking the cube root. So we could write down f of u is the cube root of u. So f prime, using the power rule, we bring down the exponent, leave the base, subtract 1 from the exponent, which gives us this new exponent of negative 2/3. In the chain rule, we're going to have to evaluate f prime at our original innermost function g. So we might want to write down 1/3 the function g to the negative 2/3 power, where g of x was that polynomial 4x minus 7. And the chain rule says the derivative of the composite function is going to be the derivative of the outermost times the derivative of the innermost. Okay, again, the derivative of a composition, f composed with g, is f prime at g times g prime at x. I probably should have given you a moment to write this down yourself. So the derivative of our cube root of 4x minus 7 is going to be 1/3 times 4x minus 7 to the negative 2/3 times 4. Now that's an okay answer, but we might want to simplify that to be a little more useful. So I'm going to think about two things. One, I'm going to think about simplifying the coefficients here. So I'm going to take 1/3 times 4 and record 4/3. And at the same time, I'm going to take care of this negative exponent and write down the reciprocal of 4x minus 7 to the 2/3. And that could be written as one ratio, where the 3 is in the denominator. Didn't leave much room there, did I? But we'll squeeze that in. Okay. One more example of the chain rule coming up. We're going to have a composition with a quotient as the innermost function. So let me remind you what that was going to be. And since I chose to write my innermost function as a function of t, the first derivative will be written with respect to t. So that had to be represented in this d over dt. Okay. So we have a power of a ratio. So my innermost function, I'll call it g of t this time, the ratio 3t over 1 minus 2t. And then I'll apply the quotient rule to get g prime. Remember that the derivative of a quotient is another quotient. The denominator of my derivative is going to be the square of the original denominator. And then in the numerator, I have this difference. Okay. So I have the denominator times the derivative of the top minus the numerator times the derivative of the bottom. You might want to pause and make sure you can reproduce this derivative. Also, go ahead and simplify it, and then you might want to hit play. Okay. Well, it turns out, as I simplify, I'm just going to be left with a positive 3 in the numerator. If I distribute the 3 above, I get 3 minus 6t. This product is going to be a positive 6t. And so 1 minus 6t plus 6t, 3 minus 6t plus 6t will reduce to 3. You can double check me on that. So that's half the derivative I need to take care of. The other half, remember, everything was raised to the 4th power. The quotient raised to the 4th. So my outermost function is going to be the power function u to the 4th. I take that derivative, and as before, I need to substitute the innermost function g. Okay. So f prime evaluated at g is going to be 4 times g to the 3rd, and that's my original innermost function. Okay. So putting it all together. Ooh. Okay. So originally we wrote our chain rule in terms of x. Now we can write our chain rule in terms of in terms of t, and the derivative with respect to t of the composite function will be a product, essentially f prime times g prime. But remember, I've highlighted this in red. We've got to plug in the original g of t. Okay, so putting our calculations together. The derivative of this quotient to the 4th power is going to be 4 times the quotient to the 3rd power times the derivative of the quotient. And this answer is okay. We could stop here. It's just harder to do calculations if we need to using the first derivative. So I'm going to recommend a couple of things. One, I'm going to simplify the coefficient 4 times 3, and I'm just going to record that over here, 12 over this denominator squared. And then this quotient to the 3rd power, I'm going to rewrite as the numerator cubed over the denominator cubed. So two things. Numerator cubed, denominator cubed, times, and then over here I did 4 times 3 and left this denominator squared. Okay. And, I hadn't even thought about what 27 times 12 would be. Better do that real quick and you'll see why. Yeah. because I can really simplify this product now. In the denominator, I have 5 factors of 1 minus 2t. In the numerator, I've got 3 times 3 times 3, which was 27, times 12, for a product of 324. And then t would also be cubed. Okay, you can pause here. That is the end of this discussion, and I hope you'll enjoy and find beneficial some practice with the chain rule.